Welcome, my name is Germán Eizaguirre and this is Primula, a practical ShuffleSort operator for serverless computing, a collaborative work between Universitat Rovira i Virgili, IBM Research and EMBL, the European Molecular Biology Laboratory. And this is an industry track for the Middleware 2020 conference. My name is Germán Eizaguirre and I am a research fellow at the Cloud Lab group from Universitat Rovira i Virgili from Tarragona, Spain. And this work was partially funded by the Cloud Button project, which is an European project for developing serverless platforms for orchestrating big data pipelines. Our work comes from a real-world problem in which EMBL and IBM wanted to automate serverless pipelines for metabolomics annotations using LitOps, previously known as IBM Pyrene, which is a serverless framework in Python. And they found a certain bottleneck during the automatization, that was that LitOps had no sort primitive. And this is a common problem with serverless frameworks. Why? Because first, serverless functions are stateless, so you cannot directly communicate between serverless functions. So, as you have the distributed sort algorithm, which is based on the MapReduce model, in which you have two stages of parallel functions that you want to communicate between each other through a shuffling stage. The shuffling stage has a lot of direct communications that in a serverless environment you have to communicate through a shared remote storage. And so, as you have a shared remote storage that is accessed by a lot of functions, the number of functions communicating with the storage system will obviously affect the throughput and the bandwidth of the storage. So finally, the number of functions you choose to use at each stage will affect the total performance of the sort, or the shuffling generally. And does a user know how many functions does he has to use for optimizing the sort time? Obviously, the general user does not know such a thing. There exists related work about shuffling in serverless environments, but usually they go against the transparency principle of serverless paradigm. Flint uses AWS SQS, which is slow and not scalable as its storage system. Pocket and Locus need the provisioning of additional resources for the storage, and such resources must be provisioned by the user and thus are not fully transparent. And Lambda and Pyrene did need the user to specify the number of workers he wants to use at each stage, so they are not transparent either. And so we propose Primula, which is a serverless shuffle operator of general purpose with a high-level practical sort primitive, and that needs no configuration parameters about the number of functions to use or the storage servers, and that predicts the optimal number of workers for sorting a certain dataset. How would we implement a vanilla sort in the original Pyrene from UC Berkeley? Well, we'll need to specify the map function and the reduce function with map calls, with calls to the map primitive of Pyrene, and the most important part, we will have to specify the number of mappers we want to use and the number of reducers we want to use. That is the key point of this work. In Primula, we remove such a necessity and we create a primitive for the sort in LitOps that only needs the name of the bucket and the dataset to sort and the column to sort it by. We have implemented it on IBM Cloud Functions and IBM Cloud Object Storage as our storage system. And how does Primula predict the optimal number of workers for sorting a certain dataset? Well, it takes into account two things. That the memory that can be assigned to a serverless function is accotated, and so we know which size of partition we can assign to a function. And secondly, that we have proven that in a distributed sort, the sort usually is slower than the in-out operation. So we can say that the sort is an in-out bound task. With this information, Primula resolves on the fly, that is, on runtime, every time the users call the sort function on a certain dataset, the optimal number of workers, instantly and fully transparently. If we know such two requirements, we have adjusted a mathematical model that calculates which worker number will give the best execution time only based on its in-out operations. And so, for that, Primula first calculates some throughput and bandwidth data between the function and the storage service the first time the user calls the sort primitive and saves such data in a local directory. Then, each time the sort primitive is called, Primula goes back to such data and performs the following calculation. Given the dataset size, it takes a range of contemplable numbers of functions, and for each of them calculates a prediction of its sort time. The sort time is divided into the map time and the reduce time, and for each of them is divided into the reading time and the writing time. And also the reading and the writing times are divided into the throughput time and the bandwidth time. For each of the cases, Primula takes the data he has already calculated about the throughput and bandwidth measurements of the storage system and defines if for the reading or the writing it would be a greater bottleneck, the throughput or the bandwidth. Performs a calculation for each of them and takes the greater one. Then sums that greater value of the reading with the greater value of the writing, and does the same for the reduce step. Sums the map and reduce predictions and calculates a total sort prediction time for each number of workers that he has contemplated. And through an iterative algorithm calculates which worker number will give the lowest sort time. This is not a prediction of the exact time the sort will take, but which worker number will give the lowest time. So we have evaluated this prediction, and as we see in a 5 GB dataset, Primula gave a prediction of 35 workers as the minimum, and the absolute minimum of the execution time gave the same. For a 19 GB dataset, Primula predicted an optimal number of workers of 52 that also gave an absolute minimum of the execution time. We have added additional features, for example, as the throughput and the bandwidth of the storage system can be saturated, straggler functions that go slower than the average can emerge. For that, we must optimize the throughput and the bandwidth of the storage system. And for that, we have performed an extensive evaluation of which file size would maintain the bandwidth and the throughput linearly for a better or a greater range of numbers of functions on IBM Cloud Object Storage, and we have determined that the best file size is of 64 megabytes. And so we perform every in-out operations in chunks of 64 megabytes. Thanks to that, we can pipeline the reading of 64 megabyte chunks with their sorting in the map stage, thus improving the execution time. And also we have implemented a straggler mitigation algorithm that launches speculatives of the slowest functions, and we have evaluated it through the generation of artificial stragglers by adding a little slowdown to their in-out operation, and we have evaluated the execution time with artificial stragglers with straggler mitigation and without straggler mitigation. And as we see in the graph, the execution time with straggler mitigation was significantly lower, and thus the straggler mitigation works fine. We have also removed the barrier between the map and reduce stages by calling the reduce functions once a certain percentage of mappers have finished, and we have evaluated the performance of Primula against other solution in a problem of 100 GB terasort. And so the total time for performing such a 100 GB terasort was similar to other solution of the literature, and thus Primula is competitive. So as a conclusion, we can say that Primula adds transparency and abstracts the complexities of the cloud to the user, that its performance is competitive with other similar solutions, and that we can accurately predict the optimal number of workers for sorting a certain dataset. Finally, I would like to add some discussion points. For example, if Primula's model could be generalized to other operations that involve shuffling, for example, a group by, then if we could use a low latency storage system such as Redis instead of IBM Cloud Object Storage, which is of high latency, as our shared system, storage system. And finally, if Primula's model could be extended to a model that calculated the most cost-effective option for the number of functions based on the execution time and the memory allocated. This was all. I hope you enjoyed it. My name is Germán Eizaguirre, this is Primula, and see you soon.